dream to dance, 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 dance. I hit the floor cause that's my plans, 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 plans. I'm wearing all my...
That was my musical interlude to your notes for today. If you could see me, I was dancing because I came to dance. All right, so a little acidic, basic, or neutral. The main idea here is all acid-base reactions. Up until now, we've just said an acid and a base makes a salt and water, which you can see in the box here that still is true. But depending on if we have a strong acid or a strong base or a weak acid, weak base, or whatever combination we have, the salt will be different. So let's take a look at the scenarios. So the first scenario we have is that a strong acid mixed with a strong base is going to result in a neutral salt, which makes sense because the strength of both of them will counterbalance each other. For the strong acid and the weak base, you can see that the acid is the strong one. Because of that, the resulting salt will be acidic. Now what that means, we'll get into later, okay? But we know acidic means production of an H+. So that type of salt will end up making an H+, but it's going to seem confusing as to right now how it would do that since it doesn't have H+ in it. We will get into that later. For now, what you need to understand is that if you have a strong acid and a weak base, that the salt that results will be acidic. If you have a weak acid and a strong base, you can see that the base is the strong part, and if the base is the strong part, then the resulting salt will be basic. The one that's hard is if we have a weak acid and a weak base, because it's hard to tell exactly which one of those weak ones is stronger, because whichever one's stronger will dominate. We won't do these types of problems because they have too many different factors involved. So really you only have to be prepared for the top three scenarios. So a strong acid, strong base combination produces a salt that is neutral, pH is 7. A strong acid and weak base is going to make an acidic salt, which will have a pH less than 7. And then a weak acid and strong base will have a basic salt, which will have a pH above 7. So the types of problems we're going to start with, and we will be using this a lot, this is very, very important, is you will be starting with your salt. Okay? If you had the actual whole equation with the acid and the base, then you could take a look at what the actual acid and base was. But you notice in these problems, they're actually starting us with the salt itself. Remember, a salt is just the substance that forms from any acid-base reaction. So what we want to do is break this thing down and go back and look at what the parents of this salt were. Okay? The positive ion, the Na part, had to have come from the base. Okay, because that's what the definition of a salt is. The anion portion, the second part, comes from the acid. So what we're going to do is go back and sort of look at where this salt must have come from. If the Na came from the base, then the base, what I call the parent base, must have been NaOH, because we know all of our bases that we're using right now have hydroxide in them. As for the acid, it must have come from HNO2. So essentially all I did for my base was add the OH to it and crisscross, and all I did for my acid was add the H+ to it and crisscross. That shows me my parent acid and parent base. And I can now look at these and tell, based on my knowledge of strong acids and strong bases, that my parent base is a strong base. My parent acid is a weak acid. If you're not sure how I got that, that is on your notes from last night. And again, you should have those memorized. So if you don't, please make sure you do. But you can see we have a strong base, weak acid combination. So the strong base is dominant. So this will be a basic salt. So again, what we do is we take our salt, we split it into its anion and its cation. We take the cation, that's the one that's part of the base, and we add hydroxide to it. That's where I got this right here. Then I'm going to take the anion, the NO2 minus, and I'm going to add a hydroxide or a hydrogen to it and make it an acid. And then just look at what those acid and bases are. So let's try this one. So SR right here, the first one always comes from the base. So crisscross it with OH minus, and SR has a +2, so that'll give you SrOH2. For the Br, I'm going to crisscross that with H, so H plus and Br minus gives HBr. Remember the 2 is here because of the balancing, the crisscrossing, but the original acid was HBr. So we have strontium hydroxide, if you think about your rules, is a strong base, and HBr is a strong acid. So that's a strong acid, strong base combination. So this one is neutral. Okay, neutral. All right, neutral salt. All right, this last one. So Ag is going to go with OH. Ag has a +1, OH has a -1. NO3 is going to go with H+. So NO3 is a -1. So that'll make HNO3 when I crisscross. So in terms of strong and weak, I have a weak base and a strong acid. That combination gives me an acidic salt. Okay. So again, take your salt, break it into its two pieces, crisscross OH with the first ion, and then crisscross H+ with the second ion, and you'll end up with your acid and your base that made it. It's kind of like working backwards, really, is what you're doing. Okay? So that's how you determine whether or not your salt is acidic, basic, or neutral. So on your predicting products, if you have a salt as a product, you would do this process. On predicting products, it'll be a little easier because the acid and base will already be written for you, but that's how you're going to end up coming up with that. Okay? All right, so let's go on to this slide. So determine if the following salts are acidic, basic, or neutral. Okay, those different ones. Those the same ones we just did? Oh yeah, never mind. I don't know why there's another slide. Okay, so let's go to conjugates. This again is another idea that is going to be important in what we're going to be moving into in this unit, what we're going to be looking at in this unit. When you have an acid, like this right here is an acid, and we write the dissociation, notice the double-sided arrow, meaning not complete dissociation. This is a weak acid, so we're going to end up with more of this than ion produced, but there is still a little ion produced. So if you have an acid on your reactant side, on the other side there is something called a conjugate base. And that conjugate base has a purpose, and we're going to eventually get into that, but for today it's just about terminology. The only difference between your acid and your conjugate base is the difference of an H+. So this right here would be considered the conjugate base to that acid because it differs in the loss of an H+. Okay, and you can see on your paper in the gray boxes below that the definition of a conjugate base is a substance that remains after an acid loses a proton, which is an H+. So once it lost its H+, you resulted in your conjugate base. So this is the acid, and it has a conjugate base. Acids have conjugate bases. Bases have conjugate acids. Okay, so acids can't have a conjugate acid. That doesn't make sense. It's the resulting solution. This right here, you may not identify right away as being a base. You're going to get more familiar with NH3 in this unit, but it is a base. Okay, having said that, the conjugate acid for this base is NH4+. Okay, so what happened was this hydrogen ion left the water and left behind the OH- from the water, and then made NH4+. This right here is the base, and this is its conjugate. Oh my goodness gracious. Thank you. I'm sure most of you already noticed I did that. So that is its conjugate acid. Again, a base can't have a conjugate base, so that was just pure stupidity on my part. So a base makes a conjugate acid. And again, what you need to be able to do is be able to identify what the conjugate is. So again, take a look at the definition of a conjugate acid, which NH4 is a conjugate acid. It says the substance that remains after a base gains a proton. Okay? There's some other examples too you see in your notes. I have them here. So here's the example we just looked at. We had an acid and its conjugate base. So for this one, here's our acid, and its conjugate base is right there. For this one, we have a base right here, and that would be its conjugate acid. That's the one we looked at before. And then here, this is a base, and this is its conjugate acid. Now, you might be asking how I knew that CH32NH was a base, and I can tell that because they gave me my reaction, and it produced OH-. Anytime you produce OH-, then you're producing hydroxide. That's the definition of a base. So you should be able to pick those out. Let's try some. So this first one, we have HCN. So first you want to write your double-sided arrow and your dissociation. So H+ and Cn-. Then you're going to label conjugate acids and bases. So start over here and figure out what this is. So this is an acid, okay? And then you want the substance on the right side that looks almost the same, but just has a difference of one H, that the H is missing. So this right here would be your conjugate base. And then, and by the way, the H plus and the OH minus are never your conjugates. So that makes it pretty obvious as to what must be. Now you look at the second one and you might say, what the heck is that? It's a big organic compound. I have no idea what that is. When we're talking and I'm asking you what the conjugate acid or base is, it's obvious that what I've given you is either an acid or base. And I hope in looking at CH33SH that you can see that this is not an acid. It doesn't start with an H. Therefore, it must be a base. So it's sort of like deductive reasoning, really. Now, with the bases, you're going to add them to water. Okay? You're going to draw a double-sided arrow. You're going to transfer the H plus over to the base. Okay? And so you'll end up with CH3, and then I'm going to do S. We already had SH, but now I have an extra H, so I'm going to do SH2, and then there's a plus charge on it. So you're not only adding the hydrogen, but you're adding a plus charge. I don't really care where you put that extra hydrogen. I put it there. If you put it at the front, I really don't care. So long as it's there and its charge is there. And then we move the H2O, a hydrogen from the H2O, so that left behind hydroxide. Okay, so that's what that equation looks like. And you should be getting good at doing that, or you should be getting familiar with doing that. If you have a base, take an H plus from the water, show the water on the reactant side. We don't have to do that with acids because we're not really concerned with that, but with bases we do. And then we have to identify our conjugate. So if this is our base, the conjugate is pretty much the same substance, just with the difference of a hydrogen ion, an H plus. So that would be the conjugate acid. Okay, so take a look at that, make sure it makes sense. You'll get a little more practice with that with tonight's homework, but that's the basic idea of it. All right, next, some more equations. So in class today we did pH and POH and all of those relationship equations, and these are some more. We are going to get into the idea of Ka and Kb, which is equilibrium, just like Kc and Kp and Ksp. But Ka is specifically for acids, and Kb is specifically for bases. So these equations we are going to use a lot in the unit. So it's important that you be able to use them. Although we haven't actually calculated any Kas or Kbs yet, you should be able to use these equations. You'll notice they're very similar to the ones we did in class today. The ones we did in class today were all about H plus concentration and OH minus concentration. Well, these ones are all about Ka and Kb, but they're very closely related, which should make it easier to memorize them. For example, if you look at this one, you know that pH plus POH equals 14, and pKa plus pKb equals 14. Or pKa is the negative log of Ka. Well, you know that pH is the negative log of H plus concentration. So you can see that they're very similar. The Ka was replaced with H's. So it's the same concept, and you'll see later on how they're related. For now, I just want you to be able to calculate with them. So this first problem says, given the Ka for a certain weak acid to be 1.3 times 10 to the negative fifth, determine the pKb for its conjugate base. Now there are a number of ways to do a lot of these problems, as we saw in class today. I don't really mind which way you do it, as long as you do it in an acceptable way. What I'm going to do is start with the equation that Ka times Kb equals 1 times 10 to the negative 14th. And I'm going to get the Kb value so that I can then go and find the pKb. So my Ka was 1.3 times 10 to the negative fifth times Kb equals 1 times 10 to the negative 14th. And then I'm just going to divide that over, and I get a Kb value of 7.692 times 10 to the negative 10. Okay, that's the first part of my problem. Now I'm going to do that pKb equals the negative log of Kb. All right, so pKb equals the negative log of 7.692 times 10 to the negative 10th, like that. And plug that in my calculator. Can't do that in my head. And I end up with, to 2 sig figs, 9.1. That's my pKb. You also could have taken your Ka and converted it into pKa, and then done that pKa plus pKb equals 14, that way it would have worked as well. Okay, and you'll get the same answer. Okay. Okay. I look forward to seeing you. Hasta la vista. Oh wait, I feel like I should have a musical exit. Hold on. I have to make sure the song is appropriate. Hold on. Okay, we'll do this one. Why isn't it playing? Hello? Oh.
I got a dirty mind.
I got filthy ways. Okay, I won't rap.